It's my great pleasure to introduce our next speaker, Dan Bedford. He's at Weber State University. He's worked for the last 20 years on climate change and has written widely on the effects of climate change in Utah and on the Great Salt Lake. He's the director of the honors program at Weber State University and a geographer by training, as am I, so it's very exciting for me. So he's going to talk to us, and then we'll have a little bit of time at the end for questions. So thank you very much, Dan, for coming.
Thank you very much, Hillary. Thank you for having me. So I'm here to talk about some of the fundamentals about climate science. We've been hearing earlier today about some of the impacts of climate change, but we're kind of still in a world where not everybody fully accepts that climate change is real, or that if it is real, if it's caused by people. There were some interesting questions that we had earlier today, kind of indicating that skepticism, and skepticism is healthy. So let's keep that in mind. As Hillary said, my name is Dan Bedford. I'm a professor in the geography department up the road at Weber State University. I came to you today via bike and front runner, so I did not drive. There were very few fossil fuels emitted on a per capita basis in the course of my journey down here today. I'm concerned about climate change for a number of reasons. One, from a personal reason. I have small children. This picture was taken just a couple of weeks ago, down in Moab. Henry there is 4, and my daughter Emma is 7. They are going to be, if all goes well, they're going to be in the later part of their life by the time we hit the end of this century, which is the time when many of the computer model projections are talking about what the temperature and sea level is going to be like. So these things are not so abstract for me. You think about what conditions will be like in 2100, that's a long way off, right? Thinking about sea level rise by 2100, thinking about temperature rise by 2100, it's pretty hard to think about that when we have a hard time forecasting the weather, and I know they're two different things, weather versus climate, more on that later, forecasting the weather more than a couple of weeks in advance. It's hard to think, really, about what conditions will be like at the end of the century. But my children will live to see it, so I have a personal stake in this. I also have a professional stake in this because this cartoon came my way about 2 weeks ago, 2 or 3 weeks ago. There's a couple watching the news, and the news anchor is there, and the punchline, the caption for this cartoon is here. So we're sort of we're living in interesting times with regard to facts. And we seem to be having a hard time agreeing on what constitutes a fact, and that we don't have a common set of facts that we can work from anymore. There is a body of work in social science that is kind of suggesting that facts don't matter, particularly with regard to contentious issues like climate change. However, there is also a growing body of evidence that suggests, in fact, that facts do matter. They're not the only things that matter, but they do matter. People's worldviews matter a lot, but facts matter too. Now, having said that, let's talk about some facts. So here are 5 things everyone should know about global warming. Now, this is opinion, by the way, these 5 things. These are not necessarily facts, but the things I'm about to point out are, in fact, fact-based. So 5 things that everyone should know about global warming are: it's real, it's us, it's bad, scientists agree, but it's not too late. These are 5 things that everyone should know about global warming. So let's start out with the first. It's real. How do we know that the world is getting warmer? Well, there are a number of ways. Some of our previous speakers have alluded to these a little bit. One obvious way, if it's getting warmer, you would expect to see ice melting. And in fact, that's exactly what you see. So we can do these repeat photography experiments where we can find photos in various archives around the world, and we can find out where they were taken and when they were taken, and we can go back to try and find the exact same spot where the original picture was taken and repeat the photograph, hence repeat photography. This is a picture from the National Snow and Ice Data Center's archives. They have a huge collection of repeat photography that you can browse online. It's really cool. So highly recommend that you can poke around here for yourselves. This is the McCall Glacier in Alaska in 1958, and this is what it looked like in 2003. Actually, I'm wondering, would it be possible to dim the lights in the front just a little bit? Because I'm not sure how well everyone can see. Can we control the lights, like back versus front? If we can, that'd be great. If not, no big deal. No, other way. That better? Can you, yep. Oh, other way. There. Okay, yeah, we'll try that. So, going back again, that's 1958, and that's 2003, right? So there's really not much question that there's been a melting of ice. And this is not cherry-picked. This kind of thing is happening, as some of our previous speakers have pointed out, this kind of thing is happening all over the world. It's not just individual glaciers. We can't go to every single glacier around the world and take photographs, but we can measure what's going on with the mass of the ice on land. We can measure that using satellites. In 2003, NASA put into orbit 2 satellites that measure the Earth's gravitational field. The mission is called GRACE, Gravimetric Recovery and Climate Experiment. And these 2 satellites measure the Earth's gravitational field to a very high level of precision. And because gravity is a function of mass, what they're measuring is changes in mass. And this is what the GRACE satellites have measured for Greenland. So it's not just isolated glaciers, individual glaciers here and there. This is showing change in mass. The bluer the color, the more mass has been lost over the last 7 years. 2003 to 2010. So Greenland and Antarctica both losing mass, not everywhere, not all at the same rate, but overall we're seeing a substantial loss of ice mass on land. We are also seeing a substantial loss of sea ice. Now, sea ice, this is frozen ocean water. That's hard to do because ocean water, of course, has salt in it, so you have to get the water a whole lot colder than if it was fresh. But at the poles, it gets cold enough to do that during the winter. And this is what Arctic sea ice extent looked like in 1981. And this is what it looked like in 2012. Okay, both measured in September, which is Arctic sea ice minimum, 1981 versus 2012. Now, you could easily say, well, that's just cherry-picked, right? Ice bounces around. Some winters are colder than others. Some winters are warmer than others. We're going to see change. There's going to be natural variability. So it turns out, however, that this is not simply a cherry-picked pair of observations. The National Snow and Ice Data Center has compiled records of Arctic sea ice extent going back to 1953. The satellite record began in 1979, and they extended it back to 1953 by doing a very careful analysis of shipping records of when ships encountered sea ice. So they can use that historical archive to estimate how much sea ice there was. And this is what the 1953 to 2013 record of sea ice looks like. So it's not simply cherry-picking isolated examples. We're seeing part of a trend in declining sea ice. You sometimes hear, by the way, people saying things like, well, Arctic sea ice expanded between 2012 and 2013. It shot up by something like 60%. Well, yeah, it did, right? Because there is natural variability. It goes up and down. And when you go from 2012, which was the record low, to 2013, there was a big recovery. Right? Would you say that was really a recovery overall? No. Right? It was from a very low level to a level that was still pretty stinking low in historical terms. It's just that it was more than what the record low was. Now, we're going to see this bouncing up and down. So if you look at individual isolated years, yes, you can say, oh, there's been a dramatic increase from 2012 to 2013. By the way, 2016 is down just a smidge higher than 2012. So that trend of declining Arctic sea ice is continuing. So we're losing ice. that's a clear signal, a clear indicator that the world is getting warmer. We're also seeing this in terms of actual thermometer measurements. So the sort of gut level obvious response to melting ice is that the world is getting warmer. Can we validate that by looking at thermometer measurements? Yes, we can. So this is NASA's estimate of what temperatures have done between 1880 and 2015. They derived this estimate by taking thermometer measurements, actual weather stations from all around the world, compiling those data and trying to kind of crunch them into a single number that represents global average temperature for any given year. That is statistically a difficult thing to do. But what they show is this increasing pattern of temperature, getting progressively warmer as time goes on. Looking at on the order of about a degree or so Celsius warming over the late 19th century to the present day, roughly a degree Celsius. Now, I mentioned that it's a difficult thing to do to crunch these numbers together to get a single number for global average temperature. It's difficult because you don't find equal spacing of weather stations. There are places that are underrepresented, like the Sahara Desert, like the oceans, like the Amazon rainforest. Not so many weather stations in places like that. You also see changes in the kinds of thermometer being used. Imagine the kinds of thermometers being used in 1880, 1900. Very different kind of thermometers, the kind of thermometers we use today. So those different kinds of thermometers have slightly different biases with regard to whether they record temperatures a little bit higher or a little bit lower than their older counterparts. So you have to take account of those changes in instrumentation. You also have to take account of movements in weather stations from one place to another, and you have to take account of the fact that maybe the land surrounding the weather station has changed. If you built a weather station out in the suburbs or the rural area, the green area outside of a city in 1900, as the city has grown, it's filled in, the land has changed, and that could affect the temperature. So there are a number of different things that scientists have to take into account when they put together a record like this. One important question is, have they done it right? Or are they biased in some way to try and make the temperature record show more warming than there really is? That is an important and valid question to ask. And this gentleman tried to answer it. His name, anyone know who this is, by the way? Nobody. Say again? This is very good. Yeah, this is Richard Muller. Richard Muller is a physicist at the University of California, Berkeley. And in 2009 or so, shortly after the release of the ClimateGate emails, anybody hear about those? A couple of people are nodding. Mr. Muller, Dr. Muller, applied for and received funding from the fossil fuels industry, particularly Charles and David Koch, who some of you may have heard of. Funded Richard Muller's study, and he pulled together an independent team of scientists at UC Berkeley, including some Nobel laureates, and they did their own number crunching analysis of the thermometer records. They were thinking, you know what, I'm not sure I really trust those government scientists. I'm going to take a look at this for myself. Now, here's what he found. He was going to blow the lid off this thing. Here is the NASA data, and he's kind of thinking, you know what, I wonder if they've fudged this. I wonder if they're kind of cooking the books a little bit to make it look as though the world is warming up when it really isn't. We're going to get to the bottom of this, and we're going to blow the lid off this climate science global warming thing. And this is exactly what he did. He got to the bottom of it, all right. This is what he found. Oh, wait a second. Pretty much exactly what everybody else has found. Now, it's not just NASA and Berkeley Earth. That was Richard Muller's group. It's also the UK Met Office, the Meteorological Agency in Japan. Pretty much everybody, when they do their independent analyses of the thermometer data, they find the same thing. The world is getting warmer. Now, this raises an important question. The Earth is getting warmer in terms of global average temperature. So you sometimes hear two different expressions regarding these issues. Global warming on the one hand and climate change on the other. What's the relationship between these two? Which term is better? Is one term better than the other? They're actually both accurate, but they mean slightly different things. So global warming means the increase in the average temperature of the Earth as a whole. Right? So that increase in temperature for the Earth as a whole on average, that's a phenomenon that we're seeing. That's what we're seeing in that increase of temperature from the thermometer data. But not everywhere is warming up at the same rate or even at all. Some places also are going to be getting wetter and some places are getting drier. That's driven in part by this increase in global average temperatures. So global warming is an accurate statement. The Earth as a whole, on average, is getting warmer. Not everywhere equally, but on average for the Earth as a whole, we're getting warmer. Climate change is a little bit more nuanced. That global warming is driving changes in things like storm frequency and intensity. It's changing things like drought frequency. So climate change is being driven by global warming. Both of those things are accurate statements, but they mean slightly different things. And I know it's a splitting hairs slightly to make that observation, but let me show you what I mean. This is an animation that shows how the Earth's temperature has changed over the time period from the 1880s to the present day. This one actually stops in 2015. This is put together by NASA based on taking all of those thermometer records and putting them onto a unilateral grid. And this is 5-year chunks relative to what's normal for each place compared to 1951 to 1980. So where you see the reds and the oranges, it's warmer than that place normally gets compared to 1951 to 1980. When you see blue colors, it's cooler for that place relative to what's normal for it for 1951 to 1980. And you can see that the warming really hasn't kicked in yet. We're in still in the 60s, and we're not seeing much in the way. We're seeing fluctuations back and forth. Sometimes you see reds and oranges, sometimes you see blues. But once we start to get into the 70s, things start to change. But again, it's not uniform. Not everywhere on the Earth's surface is warming up at the same rate, and not everywhere on the Earth's surface, in fact, there's a few places that aren't warming up at all. Most of the Earth, however, is in fact warming up. That may be a little hard to see. How well can you see that? Can you see that animation at all? Kind of? Okay. So we're at the end now, and we're seeing a lot of red and orange. What this is saying, by the way, is it's not saying that Siberia is warmer than Hawaii. Right? It's saying that Siberia has got warmer than Hawaii has. So Siberia is a lot warmer than it normally is in Siberia, which is probably still pretty freaking cold compared to what Hawaii is like. Right? Hawaii has warmed up, but not as much as the northern latitudes have. Does that make sense? Okay. So, global warming is real. It's really happening. The second thing that everyone should know about it is that it's us. This is not a natural phenomenon. This is us. How do we know that? There's a number of lines of evidence. The first one is this one. This is the Keeling curve, and it's probably familiar to many of you. Would you raise a hand if you've seen this before? Oh, not everybody. Good. Okay, so that's value for money right there. This is direct measurements of atmospheric carbon dioxide at Mauna Loa in Hawaii, and it begins in 1958, and they're continuing to do it up to the present day. In fact, I just downloaded the very latest data on the train on my way down. So this includes data right up until January 2017. So we don't have February yet because we're only just into March. But this is the most recent data that the National Oceanic and Atmospheric Administration has. And what this is showing is fairly obviously an increase in carbon dioxide over time. It fluctuates up and down because of the northern hemisphere seasons. Northern hemisphere because we've got a lot more land mass and a lot more mid-latitude land mass in particular. And in those places we have deciduous trees. So they lose their leaves in the fall and winter. They grow them back in the spring and summer. And when they grow them back, they photosynthesize a whole lot more, which pulls more CO2 out of the atmosphere. When they shed their leaves, they're not photosynthesizing as much, so the amount of CO2 goes up. So that's the little up and down fluctuations in there. But the overall picture is an increase in carbon dioxide. We're now at over 400 parts per million CO2 in the atmosphere. Why does that matter? Why do we care? Well, carbon dioxide traps heat. It's a greenhouse gas. How do we know that? Well, that's based on physical research that goes back to the 1850s. John Tyndall, an Irish physicist, is the first person who demonstrated that this was happening. His experiments were fairly crude, but they were accurate. And we've backed it up with more recent work. In 1970, NASA launched this thing. This is the Nimbus 7 satellite, and it was the largest object ever put into space at that time. It's about the size of a school bus. And it measured the amount of energy radiating off in various different wavelengths, radiating off the Earth's surface. So what's interesting about this is we can see that carbon dioxide traps heat because, theoretically, if there's nothing in the way, an object at a certain temperature should radiate a certain amount at a whole bunch of different wavelengths. And that's what these blue curves show. This is the theoretical radiation, the theoretical, it's called emission spectrum, at a variety of different wavelengths for objects at a variety of different temperatures. So this is what we would expect under sort of standard issue physical laws. Now, the Nimbus 7 satellite out in space measured something a little bit different. What it measured was this. And we can see that the energy radiating off the Earth is actually being intercepted and blocked at certain key wavelengths. So there are gaps in what we would expect to see coming off the Earth out in space, gaps right at the wavelengths that we know from laboratory work energy gets absorbed by greenhouse gases. This big dip right here, that's carbon dioxide. That's where carbon dioxide traps heat. Can people see that? No. Yeah, can we? Can't see that one. Ah, that's better. Yeah, okay, perfect. Yeah, that's great. Okay, lovely. So this is the bite that's being taken out. What you'd expect is a nice smooth curve, but you don't see that. Right? There's a big bite right here, which is energy not escaping out into space because it's being trapped by carbon dioxide. And that's being re-radiated back down to the Earth's surface. And that's the greenhouse effect. Now, carbon dioxide is not the only greenhouse gas. There are a number of others. In terms of the natural greenhouse effect, it's not the most important greenhouse gas either. Water vapor is the most abundant greenhouse gas in the atmosphere. However, we are not increasing the amount of water vapor. We are not pumping water vapor into the atmosphere. We are pumping carbon dioxide into the atmosphere. There are other reasons why CO2 matters more than water vapor as well, which I can address in questions later. But for now, we can really clearly see that carbon dioxide is a heat-trapping gas. It's not just scientists that know this. The Air Force knows this. They had to know this because in the years after World War II, as we transitioned from propeller planes to jet planes, the Air Force knew that they needed a weapon that could shoot down a jet. So they figured out how to home in on heat and developed heat-seeking missiles. Now, they had to know, they had to figure out which wavelengths of energy were being absorbed by greenhouse gases so they didn't tune their missiles to those wavelengths. So they could tune their missiles to wavelengths that were not being absorbed by greenhouse gases. That way, the missile would work. So we know from an abundant body of evidence that carbon dioxide traps heat. At a very simple level, increasing carbon dioxide means we're increasing a heat-trapping gas. The more of a heat-trapping gas you have in the atmosphere, the more heat you're going to trap. So how do we know that the increase in carbon dioxide, okay, we can see that's happening. We know that CO2 traps heat. How do we know the increase in carbon dioxide is coming from us? Again, we've got a number of different lines of evidence. Here is one of them. We can drill down into the ice cores of Greenland and Antarctica, and we can pull ice out that is hundreds of thousands of years old. The ice at the top is the youngest because it's forming from the accumulation of snow. As it gets compacted over time, gets denser, it turns from snow to ice. So the stuff at the top is the youngest, the stuff at the bottom is the oldest. You drill down, you are in effect going backwards in time. You pull the ice out, and it's got little bubbles trapped in it. And those bubbles are, in effect, time capsules of air trapped at more or less the same time as the ice was formed. So what we can do is we can take a look at what was in the atmosphere going back hundreds of thousands of years into the past. In fact, this goes to 400,000 years in the past. A European project just a few years ago has now extended that record back to 800,000 years into the past in Antarctica. Now, the graph here is showing, this is 400,000 years ago here, the present over on the far right, and what we're looking at is the amount of carbon dioxide in the atmosphere going up, going down, going up, going down. This is fluctuating naturally, okay? There are natural sources and sinks of carbon dioxide. So you might ask, well, how do we know that what we're seeing isn't all part of a natural cycle? We have natural cycles in carbon dioxide. How do we know the increase in CO2 at the moment isn't part of this natural cycle? Anyone want to say one obvious thing, how do we know? I mentioned this earlier. Take a look at the numbers here. Anyone know what we're at right now? We are, we're up there, okay? We have more carbon dioxide in the atmosphere now than we've had at any time in the last 800,000 years, okay? Some people who get overly worked up about climate change, and there's lots of good reasons to get worked up about climate change, but there are some people who sometimes exaggerate, and that's unfortunate because the facts themselves are alarming enough. You don't need to exaggerate in order to make the case. But some people mistakenly say that we've got more carbon dioxide in the atmosphere now than we've ever had, ever. Right? That's not true. We've had times in the geologic past when we've had far more carbon dioxide in the atmosphere than we have at present. But then we also had a climate that supported, dinosaurs. So it was a fundamentally different planet. This is certainly more carbon dioxide than we've had in the atmosphere at any time that human civilization has been around. Right? And that's the thing that matters. So more CO2 in the atmosphere now than we've had at any time in the last 800,000 years. This is not based on model projections or estimates. This is based on direct measurements. One other line of reasoning that demonstrates that the increase in carbon dioxide is because of us is to take a look at the atmospheric chemistry. One point here is that the isotopic composition of the atmospheric carbon is changing. So we can take a look at the various different isotopes, the flavors of carbon that are showing up in the atmosphere. And there are 3 different isotopes of carbon. Bottom line with this is that isotopes are slightly heavier or slightly lighter, depending on how many neutrons they have in the nucleus. They're otherwise fundamentally the same chemically. They're the same in terms of how they react and form molecules with other elements. So there are 3 isotopes of carbon. There's carbon-12, which is most of what we have. There's carbon-13, which is a very small amount. And if you're very astute, you'll notice that those 2 numbers add up to 100, yeah, exactly. So where does that 3rd isotope come in? Well, there's a little bit of rounding error there, and the 3rd isotope is carbon-14, which is like almost none of it. Carbon-14, the important thing here, by the way, is that carbon-12 is lighter, carbon-13 is a little bit heavier, carbon-14 is heavier still, physically heavier by a tiny amount, and that carbon-14 is radioactive. This is how radiocarbon dating works, how archaeologists figure out how old skeletons retrieved from very old archaeological sites are. Carbon-14 has a half-life of a little bit less than 6,000 years. That means that in 6,000 years, half of the carbon-14 atoms will have decayed into something else, nitrogen, I think it is, a form of nitrogen. So every 6,000 years, we lose half of the atoms of carbon-14 in any given sample. So over a very long period of time, millions of years, you're not going to have any carbon-14 left, right? So that's an important point. The reason why all this matters is because of this concept that's sometimes referred to as burning buried sunshine, which is the title of a wonderful paper by a scientist at the University of Utah that really captures the idea quite nicely. So burning buried sunshine, this is essentially what we're doing when we're burning fossil fuels. The energy that we're releasing is essentially solar energy that's worked its way through the carbon cycle over millions of years. So here's the sun, and the sun is providing energy to plants so that they can photosynthesize. They can pull carbon dioxide out of the atmosphere, pull it apart, combine it with water, and use it to build their woody tissues. And that process is driven by energy from the sun. Now, remember we've got 98.9% carbon-12 in the atmosphere, 1.1% carbon-13, and a tiny, tiny bit of carbon-14. So we've got these various different concentrations. We've got mostly carbon-12 in the atmosphere, a little bit of carbon-13, and a tiny amount of carbon-14. Now, it turns out that plants prefer carbon-12. It's lighter and it's easier to manipulate. So carbon-12 gets absorbed into a plant's tissues preferentially compared with the other isotopes of carbon. So a tree is not going to, when you break it down and look at the carbon that it's made up of, it's not going to be the same proportion of carbon-12, 13, and 14 as you find in the atmosphere. It's going to be over-rich in carbon-12. Now, when you take a plant like this, bury it under the right conditions, and leave it there for millions of years, you get coal. It's a fossil. That's why it's called a fossil fuel. Dig it up, burn it, and you're going to release into the atmosphere the same carbon isotopes that were in the tree, which is not the same, remember, as the concentration of carbon isotopes that's in the atmosphere. It's rich in carbon-12. Now, the other thing that we're going to see, remember that this stuff is millions of years old, so we're going to be losing the carbon-14. So when we burn coal, or any other fossil fuel, in fact, it's going to be rich in carbon-12 and depleted of carbon-14 relative to what you find in the atmosphere. So burn this stuff, and what you get is an atmosphere that may have a teeny bit of carbon-13, but it's going to be flooded with carbon-12, fossil carbon, basically. Now, this is what you'd expect to see. Is it, in fact, measurably happening? The answer to that question, of course, is yes, it is happening. So this is what's going on with regard to the proportion of carbon-14, the radioactive stuff. The proportion of carbon-14 in the atmosphere measurably is going down. That's because the total amount of carbon is going up as we burn fossil fuels and put the stuff into the atmosphere. But remember that the stuff we're flooding the atmosphere with is depleted in carbon-14 because this is tens, in some cases hundreds of millions of years old, fossil fuels, and the radioactive carbon has decayed out. We can see this in multiple different places. This is the South Pole. That first one was Germany. This is the South Pole, and this one is the Niwot Ridge Long-Term Ecological Research Site in Colorado. And multiple different places around the world, what we're seeing is this reduction in the fraction of the carbon in the atmosphere that is radioactive. That's because we're flooding the atmosphere with fossil or dead carbon. We can also see a change in the ratio between carbon-13 and carbon-12. Again, remember that plants preferentially take in carbon-12. So when you burn a fossil fuel, you are flooding the atmosphere with carbon-12. And what we're seeing, again, in a variety of different settings, is as the amount of carbon dioxide goes up, the ratio between carbon-13 and carbon-12 is changing. There is now less carbon-13 relative to carbon-12 than there was before. This is looking at an ice core in Antarctica, and you can see the amount of carbon-13 is dropping proportionally to the amount of carbon-12. This is in Antarctica, and carbon-12 is going up relative to total atmospheric carbon. We can see the same thing happening in the Caribbean. This is a great little research gig, going scuba diving in the Caribbean. That's a good idea. I've got to write that grant proposal. This is looking at carbon in sponge skeletons, and we're seeing the same thing, that the ratio of carbon-13 to carbon-12 is changing dramatically as time goes on. So this is a clear smoking gun signal that the source of the carbon is burning fossil fuels, because the atmospheric chemistry points in that direction. And a final point with regard to atmospheric chemistry, by the way, is that as the amount of carbon dioxide is going up, the amount of oxygen in the atmosphere is going down. That's this bottom graphic. Now, it's not going down in such a way that we're all going to suffocate. It's going down by very, very small amounts, but it is measurable, and it is indicative, again, of where the carbon is coming from. If we're burning something, we're using oxygen. In effect, the carbon dioxide is being formed by combining carbon from the fossil fuel with oxygen in the atmosphere. Remember, the easiest way to put out a fire is to cut off the supply of oxygen. So you need oxygen in order to burn stuff, and that's why the total amount of oxygen in the atmosphere is going down by very, very small amounts. Don't mean to be alarmist about any of this. It's not like we're all going to suffocate. This is a measurable indication of where the carbon is coming from. It's not a worry in and of itself. But again, it points to the fact that carbon dioxide is coming from us. It's not just Hawaii, it's multiple different places. I showed you Hawaii in that previous slide. This is on the west coast. This is Scripps Institute of Oceanography, and this is in the southern hemisphere in Australia. So this is a phenomenon that is observable in lots and lots of different places around the world. And a final point about it being us is that we can't really explain what's happened over the course of the 20th century unless we invoke the effects of increasing carbon dioxide. We do this with climate models. Climate models show that if you try and estimate what the temperature should have done over the course of the 20th century, and you only include natural effects, only things like changes in the strength of the sun, which fluctuates naturally. There's a cycle, roughly 11 years, sunspot cycle. The sun is one thing that's going to influence global temperature. Volcanoes are another. There's a number of these natural forcings on global temperature. If you only include those in climate models, this is the result that you get. Now, there are some things about the climate system that we don't understand perfectly. And there are some things about the climate system, even if we understand them, that we can't represent them very well in climate models. So the response to that is that there's many of these climate models and many groups working these climate models around the world. They each represent those imperfectly understood things in a slightly different way. And that's why no two climate models will give you the exact same result, even if they're given the same forcings of things like changes in the strength of the sun and volcanic eruptions. So each individual climate model is shown by one of these multicolored strands of spaghetti here, and that's why they're kind of all over the place. But you average them out, and you get this dark blue line. Right? So this is the average of something like 15 or 20 different climate models, each representing the workings of the climate system in a slightly different way. So let's filter out all the spaghetti, and we're left with the average. Okay, so this is what we think if the only things influencing the global climate, the only things affecting climate, temperature, were natural. Forgetting the greenhouse gas emissions, ignore those, this is what we should have got if it was natural things alone. This is what we've actually seen. So there's kind of a discrepancy there. Now, maybe that's the fault of the models. Maybe the models are just not very reliable. So let's try. If we include the greenhouse gases, how well do they represent reality? As it turns out, if you include the greenhouse gases as well as things like changes in the strength of the sun, you match reality really pretty well. Now, you take any single climate model and it could be way off, but you average them all together and the strengths in one outweigh the weaknesses in another, and you end up with a pattern that looks pretty close to what we've actually seen. Now, we cannot represent what's happened. We cannot simulate what's happened over the course of the 20th century unless we include human effects on climate. So, it's real. It's us. It's bad. Now, we've heard a little bit about climate model projections from previous speakers. I'm going to say a tiny bit more about that. Because we can't predict what future society is going to do, we can't predict what kind of technological changes are going to come along, we can't predict unusual changes in the form of government, for example. We can't predict what kinds of policies might come into place. Right? We don't even try to do that. The climate science community does not even try to do that. What we try and do instead is come up with a range of scenarios, different possibilities for what might actually happen. These scenarios are known as RCPs, representative concentration pathways. And the RCPs have a number associated with them. That number represents the amount of forcing, radiative forcing from the greenhouse gases in the atmosphere that we should be receiving on average by the year 2100, by the end of the century. So the worst case scenario is this one, RCP 8.5. That's telling us that we would get 8.5 watts per square meter of additional forcing, additional warming from greenhouse gases by the year 2100. Our best case, most optimistic scenario is our RCP 2.6. A little bit more than 2.5 watts per square meter of additional radiative forcing from greenhouse gases by the end of the century. And this is what we're seeing by way of carbon emissions associated with those different scenarios. In order to experience only 2.6 watts per square meter of forcing by 2100, this is what we have to do with regard to carbon emissions. We would have to peak sometime around 2020 and then drop off, this is globally, drop off substantially and even get negative towards the end of the century. In other words, we'd be pulling out carbon dioxide from the atmosphere. Right, so that's our best case scenario. If we want to get 8.5 watts per square meter of forcing by the end of the century, we do this. We just ramp up the amount of carbon emissions. We burn fossil fuels like crazy, like there's no tomorrow. Okay? And that could happen. Up to a point, we've been seeing that with China up until fairly recently. So that's our range of possibilities that we're currently simulating. Now, if we zoom in on this little smidge right here, these are projections out into the future starting in 2000. Now, we're already at 2017, so let's compare what's actually happened with some of those scenarios. We zoom in on that little block there from 2000 to about 2013 or so. Again, these are the different scenarios. Up until about 2004, 2005, they're essentially identical, and then they start to separate out a bit. Even by 2012, there's really not that much difference. Okay? It's over time, that's where we start to see them separating out. But over this relatively short period, you can start to see them separating out, but it's not huge just yet. Where are we? How have we done in comparison to these different scenarios? That's us right there. Okay, so we're actually doing worse than the worst case scenario in terms of emissions. So right now, and admittedly, right, this is early in the century, so there's an awful lot to play for, there's an awful lot can happen between now and 2100, but right now, we're looking closer to this than we are to any of the others. So what do those, if we put that much carbon into the atmosphere, what does that mean in terms of things like temperature? Well, RCP 8.5, which is our worst case scenario, the one that we're tracking most closely, would see us having a warming of somewhere around 4 degrees Celsius by the end of the century. 4 degrees Celsius. The World Bank put out a report not too long ago, and the title was, Why a 4 degrees Celsius warming world Must Be Avoided, because the implications are serious. So we're on track for that right now. Sea level-wise, we are looking at on the order of probably about 1 meter of sea level rise by the end of the century. That's about 3-ish feet. And there's quite a lot of disagreement in the sea level rise community, the scientists who are studying this stuff. I'm not sure it's terribly well represented in the IPCC reports, but there seems to be quite a lot of disagreement about whether that's reasonable or realistic. There's an awful lot of potential for really serious sort of black swan type events, things that we can't predict, that we don't know very well because we don't understand the workings of the Greenland ice sheet as well as we would like. So there are a number of scientists who think that the increase in sea level, this is pretty conservative, right? There are a number of scientists who think the increase in sea level could be way, way higher than this. But let's go with the conservative estimate of somewhere around 1 meter by the end of the century. What does that look like? Well, we saw some of that earlier. There was a really nice, Tyler, the student who presented first. Yeah, you did a really nice job with that. Thank you. I was very impressed with your ArcMap work. But this is from a group at the University of Kansas. And 1 meter inundation, the stuff in red would be actually underwater, right, at 1 meter. We zoom in on the Mississippi Delta a little bit, you can see what that looks like coastline-wise. The stuff in red would actually be underwater, never mind exposed to greater storm surges, but actually submerged. If we worry about something like a 2 meter sea level rise, then that's what it looks like, would be underwater. And again, there's no reason why everything stops at the year 2100. If we are on track for a 1 meter sea level rise by 2100, it's not just going to stop suddenly. There's momentum to that. It's going to keep on going. So we've got some things to worry about here. Some of these graphics you've seen from other presenters. This is Mali, capital of the Maldive Islands, and very densely populated, very low lying, and definitely at risk. This is a picture. This has not been photoshopped. This is a picture that my brother took when he was on a scuba diving holiday. So there you go, cranking carbon dioxide into the atmosphere just to get this picture. But you can see how flat, how low-lying it is. That's the same place from a slightly different perspective. Typically, it's the people who are poorest who are the most vulnerable, the people who live in harm's way. So this is a picture from the Philippines. But not always, because we also have some very rich people who are putting themselves in harm's way. There are some estimates of the total value of shoreside construction here in Florida that place the value of all of this stuff, bridges, hotels, roads, somewhere on the order of about $2 trillion. So we're also likely to see increased heat waves. not only sea level rise, but increasing frequency of heat waves. I was in London during the 2003 heat wave in Europe. This heat wave killed 15,000 people in France, 35,000 people in total across Europe. Some of that was sociological, because in France there's a tradition of everybody going on vacation in August, leaving the elderly parents behind, and consequently the care and looking after that they would normally get during that heat wave, that was absent. So you can pin some of this on sociology, on the way that certain societies actually work, but by no means all of it. I was in London at the time, and it was absolutely miserable because we're not used to it. We don't have air conditioning all over the place. This is not normal for these parts of the world. Now, could we adapt over time? Yeah, sure. We could start putting more air conditioning in. In fact, we're seeing that already. But air conditioning costs money, and so does running it. So there is a cost to adapting to this kind of change. People sometimes say, well, it costs far too much to do anything about cutting our carbon emissions. We can't possibly do that. It's too expensive. Well, not doing anything about the carbon emissions is expensive too. And for the US, actually this is globally, but some of the results are most striking for the US. This is an estimate of changing drought conditions. And this is model-based, so should always be taken with a pinch of salt, but it is looking at 22 different models and combining them so we get averages. This is work that came out of the National Center for Atmospheric Research a few years ago. And this looks at something called the Palmer Drought Severity Index. Bottom line is that the redder and sort of purpler the colors are, the drier conditions are becoming. The yellow, greener, and bluer, the wetter conditions are becoming. So as we move forward in time, you can see some fairly significant changes, particularly to Southern Europe and the Middle East, and particularly to the Midwestern part of the US. And for those of you who track things like grain production, what happens in the Midwestern part of the US should probably be of some concern. So this is what we might anticipate by the end of the century. If and the person who put this together has said that if his models are even half right, there's a huge, huge worry here. If they're even close to right, it's very concerning. What's the situation with regard to science as a whole? Well, scientists agree for the most part. Yeah, there's disagreement among scientists, there always is, but on the fundamentals that climate change is real, it's being caused by people, and it's bad news, there's a lot of agreement on this. The IPCC Intergovernmental Panel on Climate Change 2013 report, or Fifth Assessment Report, had this to say: it is extremely likely that more than half of the observed increase in global average surface temperature from 1951 to 2010 was caused by the anthropogenic increase in greenhouse gas concentrations and other anthropogenic forcings together. Now, the IPCC is actually a very conservative organization. They have representatives from it's global, so they have representatives from oil-producing countries like Saudi Arabia and Kuwait on there as well, and they can contest this if they so choose. But this is consequently a very conservative body. Many hundreds, in some cases even thousands of scientists coming together to try and agree on the wording, and as a result of that kind of having multiple voices all at the table, you're not going to get outlier voices. This is really genuinely the scientific consensus. We've now had something like 6 or 7 attempts to analyze what's in the scientific literature with regard to climate change. And all of these multiple different studies using multiple different techniques, what they're finding is that the scientific consensus on climate change is in the 90s percentage-wise. So you look at the scientific literature, what percentage of them go along with the scientific consensus position that global warming is real, caused by people, and bad news? It's in the 90%. It varies a bit depending on exactly how you do the study, but that's where it is. And that's what it looks like, that there are maybe 3% that aren't in agreement, but 97% that are. And we have a problem here because that message is not widely recognized in the general public. So we have something of what's called a consensus gap. 97% of climate scientists agree, but the public thinks it's only about 55%. But it's not too late. This has all been a bit doom and gloom so far, but it really isn't too late. And here's a couple of optimistic points just to leave you with. This is a back-of-the-envelope study that calculated how much land area would you need if, using current technology, if we put solar panels on this much land area, that little black square right there in the Arabian desert, if you covered that with solar panels using today's technology, today's efficiency, you would generate as much electricity as the entire world uses. That's what it would take. Now, you couldn't actually do it this way because there's transmission losses and so on. You can't make it all in Saudi Arabia and then send it by high-capacity cables all around the world. But there are ways that you can do it. Even here in Utah, this is work from the Solutions Project at Stanford University. And they looked for every single state. They looked at what it would take to convert the entire energy system to 100% renewables, wind, water, and solar. And it would create 29,000 jobs, and it would save $7.8 billion in mortality costs, people dying early and getting sick from air quality problems. And you would get in your pocket by 2050 an average annual energy cost savings of $127 per person. So you would save money by doing it. That's per person. Plus, the cost of energy by 2050, if we stay with fossil fuels in Utah, we'd be spending 9.02 cents per kilowatt hour. But by 2050, if we stay with renewables, we'd be spending 8.88 cents per kilowatt hour. So it's cheaper. Bottom line, global warming is real. It's caused by us. Scientists agree it's bad, but it's not too late. If you're interested in learning more about this, I have a book out with my co-author, John Cook. The book is called Climate Change, Examining the Facts. And we're also having the Intermountain Sustainability Summit up at Weber State University in about 2 weeks' time. It's March 16th and 17th. And John Cook, who founded skepticalscience.com and also did the 97% consensus survey that I mentioned earlier, he's going to be there doing a workshop on misinformation. And this woman, Mary Robinson, is going to be there, former President of Ireland, former UN High Commissioner for Human Rights, and founder of a non-governmental organization called Climate Justice. You can register and find out more at intermountainsustainabilitysummit.com. And I think we're out of time, so I'm going to hold off on questions, maybe talk with people afterwards.